Okay, good morning. Good morning, everybody. And as usual, I'll ask if you have any questions about what was discussed in the last lecture, or even earlier, whatever questions you have, you can do that. Okay, so the lecture must have been very, very clear. So no questions.
So say when I am in the, say in 2D Ising model, if I am in the ferromagnetic case, then no matter what configuration I start with, if I wait for a long time, it should go to like this state with all spins aligned, right? All the domain walls should.
Domain wall should disappear. If you start with the state which domain wall long enough, it will go to either negative or positive or negative.
So I have a question. Now suppose I have a torus geometry of the sample, and now my domain wall is like this. So through small deformations, it won't be able to go away. Only this kind of loops will be able to go away. Not this or this kind of loops, right?
Not quite sure what you mean. I mean, your domain wall is now
extending around the sample, the torus, like this, like this. So through small deformations or through local spin flips, it won't be able to go away, right?
What is that? I mean, there is no conservation in the model. So spins can flip depending on how the
What can break the domain walls is stable or can self-align? Is that the question?
So there is just one domain. Suppose this is the.
Whether they disappear.
With one domain wall you only do it because you have a torus and then the spins are up here, down here, but then you can go around like that. You need two walls.
No, but if you are not at zero temperature, non-zero probability of breaking the wall,
Breaking the wall,
break it locally. At many
There is
places.
no topology. I mean, you have a line there, line can be broken.
Exactly. At a finite temperature. Zero temperature you can't do.
Yeah.
So there are situations, for example, if you, I was just talking about one of those, I think, but aside, that if you are looking at binary alloys or things like that, and if you're mapping that to an Ising model, then there is conservation. Magnetization has to be whatever it is at the beginning. So when the magnetization is zero, you start with a state like that, then there has to be a domain. There has to be the plus and minus. So there will be phase separation. The plus will all go one direction and minus will go another direction. Okay, so I was talking about Ising model. Ising model in one dimension. In particular, we were looking at correlation functions. That's a new thing that I introduced last time, which is by itself is it's not a thermodynamic property. This tells you about how spins which are separated by some distance, to what extent they are correlated with each other. And we found out that for the 1D Ising model, one could calculate this correlation function explicitly. And the result was that there was basically an exponential decay with distance. There was a length scale associated with that, which was the correlation length. So I mean, that's really not special to the one-dimensional Ising model. I mean, in any spin model in any dimension, you can define this correlation function. The correlation function will decay in the paramagnetic state. Correlation function will decay as a function of distance, and there will be a length scale associated with that.
I have one more question actually. So, like we calculated the correlation function last day. Now suppose that I am in some general spin model, and I want to calculate a correlation function. So I propose a scheme that say like the term is G like sigma I plus L.
Right.
So I suppose I add a term in the Hamiltonian which is some G times. So I'm saying that in the Hamiltonian, let's say I add a new term, which is like G times the summation over I sigma I plus L. Then for this new Hamiltonian, I do all the calculations and then I take the derivative with respect to S and then set limit G tends to 0. So is that a valid?
Yeah. So now G tends to 0, the field that you have put. When you see there's a new term in Hamiltonian.
Yes.
Right? And that is a coefficient.
Yeah, exactly. G, that's what I'm
That's what you're putting.
Yeah.
Yeah.
But what if that new term resulted in a phase transition? Then the limits would.
So I mean, I will do something which is exactly similar to what we are talking about. So there is a term in the Hamiltonian, usual thing, not I and I plus L, but sum over I sigma I, which is the magnetic field.
For magnetic field.
So if we take two derivatives with respect to that, then we become this coordination function. So that's precisely what I'm going to do today.
But is that generally valid, like for calculating the correlation?
Well, when that term is non-zero, then we don't have a phase function. In this particular case, when there is a magnetic field, and the field is non-zero, the symmetry is already broken. There will be always magnetized in the direction of the field. So you can look at that limit h going to 0, and that gives you coordination functions and so on and so forth, as we just said. But if the coefficient of the term is finite, then, at least in this case, it will destroy the phase function.
So like we were discussing, like if you say add such a term in the 1D Ising model, then that would add long range interactions, and that might in fact add.
Yeah. Again, there is a good observation that
one
on the Ising model, when I said there is no phase transition, that is true only when you have short range interactions. If you have interactions that this follow as a power of distance, then depending on the power of that, you may or may not have a phase transition.
So then I should not use this scheme that I just proposed. In general.
Not something that is exactly, not I and I plus L. You apply a field, which is a very legitimate thing to do. But then that will include all pairs. So, and if you include all pairs, then there is an interesting relationship of that with the susceptibilities. That's what I'm going to work out. In the sense that magnetic susceptibility is related to coordination functions. How to relate susceptibility to coordination functions, that's something which is important. Okay, so let's just start with some generalizing models. What I'm going to say is actually mostly valid for other models also, but the Ising model is here to deal with putting vector science and things like that. So we'll do the calculation of the Ising model, and then we can discuss to what extent that is valid for with the spins at not just plus minus 1, but vector and things like that. So again, I'm looking at the Ising model. You have a Hamiltonian, which I've written down earlier, minus time coupling constant, let's say nearest neighbors, sigma I, sigma j, and then now I put in a filter. So that gives you UB times H times sum over I, sigma I. This is my Hamiltonian, right? So, just an aside, what I did last time was where I put H equal to 0, just the interaction at term of. And there are two lines of algebra that will give you the partition function and so on. You can generalize that calculation when the full field is not 0. But there you have to do a little bit more. You write down a transform matrix of that, look at eigenvalues of the transform matrix and so on, which can be done. So, with or without field, the 1D Ising model is actually solved. But I'm not going to solve the Ising model now, but point out certain nice features that relates the magnetic susceptibility to the coordination functions that I had introduced last time. So to do that is again reasonably simple. So let me just make it notation fixed. The magnetization M is basically mu B times sum over I, sigma I. Right? Sigma I average is the average value of chemical spins, and this averages will be non-zero when this H is non-zero. We say that there is no dominant order, so it says that sigma I average when there is no field. That will be zero always at any finite temperature. But now when you put in a field, that again becomes similar to, for example, when we have a paramagnet, you put on a field and that gives you a magnetization. So similar thing will happen here. As long as there is a non-zero field, there will be a magnetization, but that's an aside. And when you define susceptibility, will be defined as H at constant temperature. This is your magnetic susceptibility. So let's see what this M looks like when you write it up. So this M is equal to mu B is outside, that doesn't matter. And then you have to look at the average value of this quantity. So this will be two terms. Downstairs we have a partition function, which is sum over sigma I. Upstairs we have again sum over all sigma I. But now you put in this one, sum over I, sigma I, and then and H is basically what I have written down over there. So, so this is my magnetization. If I want to calculate susceptibility, then I have to take one more derivative of this. Right? So where does the derivative come from? It comes from the Hamiltonian. Hamiltonian involves this H field. So when I take a derivative, I pick up basically, when I take a derivative, I pick up mu B times sum over I sigma. Where does H occur? H occurs, little h occurs in the Hamiltonian. So now, if I want to calculate this phi, given this expression for M, I will just do the derivative of this with respect to H. When I do the derivative with respect to H, so this quantity e to the minus beta times Hamiltonian has a term which is e to the beta mu B H sum over I sigma I. This is coming from this Hamiltonian when I look at e to the minus beta H here. So when I take a derivative with respect to H, then I bring out this factor beta times mu B times sum over I sigma I. Okay? Now H appears, little h appears here as well as here. So there will be two terms when I take a derivative. One is coming from the derivative of the upstairs and the other is coming from the derivative of the downstairs. Yes? This is just a simple differentiation that I am doing. So the result is, so there will be always a beta times mu B coming in whenever I take a derivative. So there is a, so now if I calculate this phi, which is as I written down over there, this would be equal to mu B squared 1 over kBT. This is basically coming from this beta times mu B. And then there is a factor of sigma. But sigma has to be put inside because basically we are basically doing a sum over all the sigmas. And it is fairly easy to show that this is going to be two terms, sum over sigma I, numerator, this is just coming from the derivative of the numerator. When When I take a derivative, then since here we have this sum over I sigma I, and already there is a sum over I sigma I sitting there. So it's sum over I sigma I, this whole thing squared. And then there will be another term that comes from derivative downstairs, because this H itself has little H in it, and that will be again this derivative algebra. So again, just a little bit of algebra. What I'm doing is that I'm taking a derivative with respect to H in the H that appears here. So the numerator remains the same, and this is basically one factor. Might be a little bit of confusion coming from this, what I'm writing here and what I'm writing over there. So this basically means that I have to sum over all possible values of this sigma i's. And this is just a straightforward sum over I all the space. So when I'm this I call trace earlier, but people get confused. So explicitly I am writing that this rotation here basically means that whatever is inside, you evaluate it for different values of this sigma I, and then sum over all possible configurations of this sigma i's. So this is something that you can easily verify for yourself. Just triangular differentiation. That we differentiate the numerator, then you get sum over I sigma I squared, its average value, and then when you differentiate the denominator, then you pick up sigma I average, sum over I sigma I average, whole thing squared. So the outcome is basically this is mu b squared. What I have here is just the average value of this quantity. So sum over I sigma I is sum, then square it, and then take the average. What I have inside is the individual spin average, sigma I average. So you take the first average, then sum, and then take the square. So it's just state review. This is just following from the fact that your definition of the magnetization involves this quantity. And then what I'm doing is just using that definition and taking one more derivative with respect to the fifth term to get this susceptibility, which is this one. So one can rewrite this in a very simple form. Mu b squared plus anything. And so there is sum over I sigma I and then whole thing squared. So this I can write as sum over I and j, sigma I to sigma j average. And the other term here, the first take the average and then sum and then square. So then it will be sigma I average. Right, so basically what the susceptibility is doing, according to the usual definition, is that it's basically sum over all such correlation functions. Sigma I, sigma j average, this is something that I defined in the last lecture. This discusses about the correlation between spins located at site I and site j. And this is basically the product of the averages. So again, this is in some sense a measure of correlation. Whenever you have two fluctuating objects, when the average of their product is different from the product of their averages, then says that these two things are correlated, these two things are not independent. Right? So So in general, the correlation function will be defined like that. For the case of the one-dimensional lighting model, I didn't write down this term because this term is zero. One-dimensional lighting model, when there is no external field, sigma I average, sigma j average is a zero. So it's just a term that involves the product of the spins and average of that. But in general, when there is a magnetic field or when there is a ferromagnetic state or something like that, sigma I average, sigma j average will not be zero. And then you need to subtract out that quantity from the average value of sigma and sigma j. And this kind of correlation function is, there is a technical name for it, it's called a connected correlation function. That we look at fluctuations in this sigma I. So this is actually, can be written in the following way. Sigma I minus sigma I average sigma j minus sigma j average. And then you take an expression there. This quantity is called a fluctuation. The actual value minus its average value. So this is a correlation of fluctuations of spins located at different sites on the lattice. And this is the right kind of correlation function to look at. This is what will go to zero at known distances. So you see, if you have a ferromagnet or a magnetic field, then sigma I, sigma j average will not go to zero even if I and j are very far from each other. If they are very far from each other, they are not correlated. So sigma I, sigma j average will be sigma I average multiplied by sigma j average. And if this average is non-zero, then we get a non-zero value. Correlation function will not go to. That's one way of defining order actually. In the correlation function, if I look at two sites which are very much further away from each other, if that correlation function does not go to zero, as the distance goes to zero, then we'll say that there has to be some kind of order, because that basically means the individual averages themselves are non-zero. So this is actually an important result. It relates the susceptibility, which is this quantity, to correlation functions. And correlation functions is not just one correlation function because we are summing over all spins I and j. So it's basically integral of the correlation function over distance. And the actual correlation function to look at is just not this, but this connected part. Which is basically you subtract out the product of the averages to get something which is about actual correlation of fluctuations. So, and this is not valid just for the Ising model. As you can see here, if you had a Heisenberg model or something like that, then these sigmas will be replaced by the spins. But this procedure that I have gone through, that is valid everywhere. Because the spin will couple to the magnetic field in a similar way. And when you take two derivatives, one term gives you the product of the two spins at sites I and j, the other is the product of the averages of these spins at sites I and j. Okay, so this says that there is a relationship between, so what is this phi? This phi tells you is called a response function. Why is it called a response function? You are, this is your original Hamiltonian, this H you introduce externally. So it basically tells you about how the system responds to introducing this kind of a perturbation. When you turn on a small field, that basically says that you are now adding another term to the Hamiltonian, and the field is coupling to the magnetization. That's how the magnetic field in this case looks like, right? This quantity, as I said, is the magnetization. So, and then you measure the magnetization and find out how much magnetization has changed. So it's basically a response of the system to some external probe, which is the probe is basically here, the external magnetic field that we introduce in the probe. Delta M, delta H basically means whenever I change a little bit of H, then how the system magnetization changes. So it basically, that's what you mean by response function. Response function, you perturb the system by something, small perturbation, then there will be some small change in the system, and then you want to find out how much the change is related to the actual perturbation. And here, we are looking at a linear response. M, this delta M divided by delta H. So this is actually a linear response function. And in general, there is a very beautiful framework in statistical mechanics which relates this linear response, this is called a linear response chain, and it relates the response function to correlations, fluctuations. There's things called fluctuation distribution theorem and all that things that you can eventually derive in the general framework. But I don't want to go into all those details, but it is important to keep in mind that this kind of response function is related to correlations. Correlations of what? Correlations of fluctuations. So what I'm looking at here is just this response function. What I'm looking at here is the correlation in the fluctuation of the sigma variable and how they are correlated over space. And you are doing basically the sum over all such layers, which in turn means that you are basically doing an integral if you want to transfer that to a continuous expression. Okay? So this is something that you should keep in mind. That this is something that is useful. Physical meaning, for example, of what this response function means and how to relate that to correlations, etc. How do you measure correlations in general? I mean, is there any idea about, if I want to look at a system and if you want to look at correlations, what kind of spatial correlations are there in the system? So when you look at a magnetic system, you want to find out what kind of magnetic order is there in the system. Can you name an experiment that you do to prove that, answer that question?
Neutron spectroscopy.
Yeah. What does it do? I mean, it looks at neutron scatter from the spins that you have in the system, and from there you get some information. What information do you get?
We send in neutrons of particular momenta, and then we see at what value of momentum do we get a peak in response.
You look at the scattering cross section as a function of momentum transfer, right? So look at something that depends on neutron coming in this way and then it's going out that way. So there is some transfer of momentum, and if you then you basically look at the cross section as a function of that transfer of momentum, delta K. And if you look at the actual theory of neutron scattering or light scattering from liquids or whatever, it basically measures spatial correlation functions of the quantity that is coupling to the probe that you are using in your scattering experiment.
So we can get the when the neutron is scattered, we know what kind of fluctuations there are in the system with which momenta. Then we convert back to real space to
Yes,
see
so
the
we get the information in Fourier space because you are looking at delta K being the K out minus K in. And then, so the result that you get also is a function of that. So get real space information, you then Fourier transform back to real space. But the quantity of which the Fourier transform we are looking at actually is a two-point coordinate function. It's a correlation function of the quantity that couples with the probe. So why do you need neutrons to look at magnetic order?
We need neutrons because let's say if we have electrons, then it won't be able to probe the magnetic structure because the Coulomb repulsion is so high. It won't be able to see the inside
The
structure
probe
of
itself has magnetic moment. Neutrons have magnetic moment. That's a zero chance. But it will, when there is a magnetic moment, it will couple to the local magnetization. It will prove the local magnetization. So if we are looking at just the density, which I mean, in a liquid, for example, there is also density correlations. If you want to look at those correlations, then you use a probe that couples to the local density. Then you can use light scattering. I mean, there is no neutron speciality because it probes the magnetic structure. So it couples to the local magnetization.
So this would be polarized neutrons.
Yeah.
For pressure, what did you say? If we want to measure the density correlation, what kind of probe would we use?
Anything that couples to density, And typically one uses light scattering.
Oh, I see.
Light scattering couples to local polarizability, which again depends on the local density.
What about using some kind of pressure wave that can something like that be done?
You have to use something that basically can go inside the system to some extent. So light, neutrons use, I suppose V1 scattering people use, physics is a little different. But general scattering experiment, one measures coordination. Coordination function is a coordination function of the quantity which couples to the probe that we are using in the scattering experiment.
So, for example, in this case, we have the spatial correlation function. When I go to Fourier space, it means if there is some fluctuation with what dispersion it will travel. Is that?
So, I mean, that's what you tell me now. This correlation function we found out last time is also exponentially in distance. E to the minus r divided by z. Take a Fourier transform of that, what do you get? Certainly will depend on the dimension. Do it. And that will tell you how to measure this size. So you can look at it as a function of k and then look at how it falls out as k increases. There will be something in that. And that will tell you what the coalition length is. Okay, so let me just carry this to completion and then we'll see that some of the results that I derived earlier can just follow from this. So everybody has taken it down or whatever I can read it, right? So this M of course is an extensive quantity, it's proportional to the volume of the system. So typically one deals with something that doesn't depend on system size. So I define, let's call it by tilde, which is this pi divided by the number of spaces that you have in the system, which is equal to 1 over n h. And I have written down an expression for this last time. So this is equal to 1 over n mu b square over k t. And this quantity that I have written down last time, sum over ij, all spins sigma I, sigma j average minus sigma I average. So this is a general result, valid for 0H, non-0H, whatever. But now one can sort of see how to, one can write it down in somewhat simpler form. So basically now let's just look at a situation when one is looking at a paramagnet, one is looking at a paramagnet in zero magnetic field. So sigma I average is 0, right? So I'm looking at this standard paramagnet that I talked about in my first lecture. So then this average is as 0. Right? What about sigma I, sigma j average? In a paramagnet, what do you expect? Paramagnet, there is no interaction. So each spin is just saying the external magnetic field. There is nothing that connects one spin with another spin. Right? So sigma I, sigma j, when I is not equal to j, that average will be 1. That will be 0, right? So only the I equals j term. Now for the Ising model, sigma I squared is equal to 1. So this then becomes 1 over n mu b squared n just n. Because this term is 0 and this is non-zero only when sigma I is equal to sigma j. In that case this is equal to 1 and then you have to bring this sum and that will give you a factor of 1. So this n and that n will go together. So we get the result, the zero field susceptibility of a paramagnet, I think paramagnet, is going to be just mu b squared over kVt. So is that expected or unexpected? Yeah, I mean this is something that we had put out earlier, but general less. But now if you in that formula, you just go back, put s equals to half, and we will find out exactly this result. That Ising paramagnet in zero field, that susceptibility looks like about 1 over 2. Now if I put on turn on the interaction, as I have done in the Ising model, one-dimensional Ising model, that's what we have done. The interaction term is non-zero. There again sigma I average and sigma j average will be 0 in zero field. So now we look at second case, which is 1D. Okay, questions? One D Ising model is equal to 0. There again, this average is a 0. But this will be non-zero. It will depend on the distance between I and j. Yes? And then we have to sum over all pairs. So without much ado, I can just write down the result for that. So for this, we will have mu b squared over kVt, and this sum I can first keep I fixed, sum over all j. That basically means take a particular spin and you are summing over all distances on one side, all distances on the other side. And if you have a system that is infinitely large or periodic boundary condition, then that will not depend on what the initial side is to. You get the same sum for all values of I. So basically, I have to put the sum over j, and then sum over I will give me a factor of n. So this n and that n will cancel out, and we will basically have sum over j. Let's call it sigma 0 for sum over I. Forward, then yes, a little more complicated than that. So let me just take it out separately. So here I is equal to j, that gives you 1. Right? So there will be and sum over these two indices. As I said, I can break it up into keep one index constant and sum over all the other indices, and that will not depend on what the initial index is. So there will be a term which is 1 plus sum over some distance is L and tangent j raised to the power L, and this L goes from 1 to infinity. What does it come from? And I hope you are understanding what I'm doing here. I put this sigma I average and sigma j average is to be equal to 0. That term doesn't contribute. I'm just looking at that 2-point coefficient function. 2-point coefficient, the sum, when you sum over both I and j, sum, if I keep I fixed and sum over j, then I get some value. And that doesn't depend on what I you have chosen, because it's an infinite system. So that sum over I basically gives you a factor of n, which I cancel out with that factor. And then the sum over j, sigma 0, sigma j average, there will be one term which is j is equal to 0, that will give me 1. And then there will be terms which are separated by some distance L. And we found out that the coordinate function just looks like a hyperbolic tangent, something next to the power L. So I'm summing over L equals 1 to infinity. But there is another factor you should catch. There is another factor that we should put in there. So, I mean, if I draw this picture, then everybody will know. So there is one side here, and I'm summing over all these other sides. So this is L equals 1, this is L equals 2, etc. But there is also the other side. So, I mean, this L is not that. So there will be one here, one here, one here. This is again another L equals 1. So just have to put in a factor of 2. Saying that any side, you put in basically the right neighbors, and then we look at the left neighbors. Yeah? And this is exact. This is something that just follows from the definition of susceptibility. Susceptibility in terms of correlation functions. Correlation functions I have calculated. So I just put that back in here, and that gives me basically this expression as an infinite sum. But this infinite sum can be summed because it's just a geometric space. And so the final result is this. If this called over T, and when I do the sum, so I'll get 1 plus 1 minus plus. Hyperbolic tangent j, divided by 1 minus hyperbolic. So this is an exact result for the zero field susceptibility of the one-dimensional answer. That it depends on temperature. Dependence like this. There is something that tells me that near low temperatures, this will have some interesting behavior. What happens? I mean, if this is exact. So, I mean, take beta goes to infinity, t goes to 0. Hyperbolic tangent, when the argument goes to infinity, it goes to 1. The denominator goes to 0, and there will be divergence as the temperature approaches 0 temperature. Is that surprising or not surprising?
Zero temperature, the system would like to be in the ground state. So
Yeah. Magnetization would be plus 1 or minus 1. And this per spin will be plus 1 or minus 1 at 0 temperature. At any finite temperature, it is 0. So as one is approaching 0 temperature, one is approaching some kind of an order state. Finite temperature, there is no order state. But as one is coming towards 0, then approaching more and more order states. How do we see that? We saw that in the correlation length. Correlation length was the exponential of 2j divided by kBt, which itself diverged as t goes to 0. So in the one-dimensional logic model, there is no finite temperature phase transition, but there is something special about the 0 temperature point, saying that as one is approaching that, as one is going to lower and lower temperatures, your correlation is becoming longer and longer range. And there is more and more short-range order, so to speak. And since the susceptibility basically is an integral of this correlation function, the correlation function, when the correlation becomes long range, the integral is very. So So susceptibility itself diverges as one goes to zero temperature, and one can work that out very easily. There is a so this goes to mu d square over kBt exponential 2j divided by kBt as t.
So here, at zero temperature, we have some kind of divergence. Can we do a sort of critical point study, even though we have only
Yeah, so I mean, Ising model, you say that there is no phase transition between finite temperature, but it approaches a phase transition as t goes to 0.
So we can calculate the exponents for this.
Are there exponents? I mean, here, what do you say exponents? The exponential 2j over kBt. I know the correlation length. It's diverging. It is not diverging as a power. Susceptibility also is diverging. It is not diverging as a power.
But in general, if it's only from one side that we can approach that point,
Yeah, so
then
this
we
is not like an ordinary critical point. There is no ordered phase. Critical point says that at this side, at temperature you have a disordered phase, and on this side you have an ordered phase. And so the phenomenology of this is quite different from what you see in standard critical phenomena, but the qualitative behavior is similar in the sense that you have a susceptibility and a correlation element, which are diverging as one approaches the critical point. You cannot go below the critical point. You can approach it from the bottom.
If you think of a dimension interpolating between 2 and 1, and which people do, 1 plus epsilon, then Tc drops as a function of epsilon and becomes 0 only at one dimension. So it's really Tc at 0.
That we will see in other spin models also. For example, instead of looking at Ising model, if I look at XY model or something like that, even there will not be any phase transition at any finite temperature, but there will be again a correlation length which will diverge as t goes to 0, but not in this exponential fashion. That is also interesting because where does this exponential function come from? What happened?
Nothing. Whatever.
These are things that, if you think about it, it becomes kind of obvious, but at the beginning, it's not obvious. So this exponential function comes from the fact that if you look at the down state and look at the first excited state, there is a gap. Whereas if you have continuous states, then you look at a ground state where everything is aligned. But the excited state can be arbitrarily close to the ground state. Because if you rotate a little bit, one spin a little bit, and things like that. Those things, so those are, there's a continuous spectrum of excitation. So whereas here, first excited state is separated from the ground state by whatever, 2j or 4j or something. That leads to basically this exponential kind of scaling. But the general characteristics that I want to emphasize is that there is, first of all, I mean, what was it there in the previous board, that there is a exact connection between the susceptibility, which is response function, with correlation functions. And if you know how the correlation function behaves, then you can calculate susceptibility. And if I do that from the Ising model, we'll find out that there is a divergence of the susceptibility as it approaches zero temperature. And this divergence is related exactly to the divergence of the correlation length that we have calculated last week. Yeah, so one can learn a lot of things. Just Ising model is sort of a 3D model because it's easy to write down, and many things that you can do with the Ising model that are difficult to do for other systems. But one can learn a lot of things just by looking at the Ising model, simplest model. Okay, since we are on this topic, I mean, this on this topic in some sense. We're just talking about ground state and excitations and so on. Let me just do another simple model in one dimension. And there we'll see that how these things depend very quickly on the kind of spins that you have in your system. Ising model, basically the discrete model. Its spin can be only two values, +1 or -1. So up or down. And so, as I said, the excitation spectrum has a gap. If I now look at continuous spins, what do I mean by continuous spins? Where the interaction, the spins are not just two discrete values, but it can take a continuum of values in some way. So let's just look at another simple model. Now, not Ising model, but I'll call it XY model. This is one day. So now I am introducing spins which will have two components. So I talked about this, Ising model just as one SZ, and then Heisenberg model X, Y, and Z. But XY model has only X component and the Y component. And I will look at, for simplicity here, the classical model. It's just, let's say unit spins, which are sitting on a lattice. And basically, degree of spin is like this. That you have some spin which can be anywhere on this circle. This angle is theta, and let's call the length of the spin is S. So Si is one of these vectors. Vector of length L, vector of length S, and it can be anywhere in this circle. Same radius S. So if I now look at side of this J, this I can write as minus J, and each spin has magnitude S, A squared, sum over magnitude pairs of J, cosine theta I. Theta is the angle that the spin makes with some arbitrarily chosen x-axis. Cosine is just an angle between 1 and 2, so it's just a difference between theta I and okay, so again this J is positive. So basically it says that the ground state will be one in which all the thetas are the same. This is the aligned state, fully aligned state. One dimension, you have a chain and you have this vectors sitting at individual sites, and the energy will be minimized when all of them are pointing in the same direction. But is this state this unique state, or how many such states are there? It can point in any direction on the circle. So that's again another difference. In the Ising model, there is only two ground states related to each other by a discrete symmetry. But here there are infinitely many ground states related to each other by simple rotation. Ground state is infinitely limited. So that's one big difference between models with discrete spins and continuous spins. But now when we go to higher temperature, do we expect this model to order in one dimension? Discrete model doesn't order, right? I mean, Ising model you said you cannot order at any given temperature. What about this one? It's more difficult to order systems with continuous spins, so I would say that it will not work. But can you, so what I want to do is just want to do very simple calculations of this excitation. The Ising model, what we did, we looked at the ground state and we looked at the first excited state. First excited state was one when we had a kick. On this side, if the spins were up, on that side, the spins were down. And there was some finite energy, 2J at the physical time. Then we said that this king can be anywhere, so the entropy always overrides the energy in the limit of large system size, and so it doesn't work. But what kind of excitations you expect? That will basically, that would be local excitations. But what I want to look at the excitations that will destroy the object. T equals 0, you have everything lined up. So I want to have situations where I have an excitation which is present, will destroy this alignment.
The same thing, but infinitesimally like something.
So if that will not destroy it. So if you, this is something that you need to think a little bit about. So we are saying that on this side, let's say one is up, and on that side we are getting it like that. Is that what you had in mind?
Successively small going down. Not just like.
So this will not destroy order, you see?
No, not
If
this.
it is just a little bit tilted, then that's somewhere over that is, then there will be still something remaining in that direction. So you have to have a situation where the fact that you have up on this side is cancelled by having something which is down on that side. So then you have average over this, then presumably your sum over I is going to be equal to 0. The second is domain 1. As in model, we needed a domain 1. Single spin excitation would not destroy order, five spin excitation will not destroy order. It needed domain 1, whereas macroscopically we have positive on one side, negative on one side. So here also, what we want to look at is the domain 1 that looks like this, where spins are up on this side and down on that side. And then we want to find out what is the configuration of the spins in between, which will minimize the excess. And as you were saying, it's intuitively pretty much clear what is going to happen. Instead of just creating a short domain 1, where everything is on this side up and everything on that side is down, that we'll see. Energy of that will be of order of J, right? Where you are breaking the bond, right? One side is up, other side is down. But here you don't have to do that. You can spread out, so one is changing the angle by pi. Right? And here, the angle will be slightly different from this, and slightly different from that, like that. So this whole thing will rotate and then become down a dollar.
In this case, because we are rotating like this, is it fair head order towards the right?
You can't do it. Let's see. So So what I am doing here is basically delta theta I plus 1 minus theta I is pi divided by Right, man? So here the angle is changing from by known amount of pi, and you are dividing this change equally into all pairs. So just do the calculation. You look at instead of Z.
What I mean to say is the spins are lit up at the leftmost point and we are rotating by pi in the clockwise direction to get a downspin. So throughout the chain, there is no spin pointing towards having any component towards the left. All of them have a component towards the right. So we can we not add up all those components to
Your cosine theta average, when you are averaging continuously between 0 and pi, will give you 0. sin theta average between 0 and pi will not be useful.
But the interaction is
So as far as I remember, the third law of thermodynamics says that at T equal to 0, the entropy should go to 0, right?
Yes.
But you just said that there are infinitely degenerate ground states,
Yes.
and at T equal to 0 it should be in the ground state.
No.
So there is
no contradiction because they have to be accessible. In the sense that what you're saying is that all the rotated states, they are also accessible. That a particular system can go from one to the other and other. There would not be any phase transition at all. Yes, the fact that there is a phase transition basically means that there is a spontaneous breaking of
but
symmetry.
here we don't have, right? So here we don't have.
Oh,
so we
here
can
we-
access all the ground states
Yeah.
without.
So that's it.
So like then the
That's
entropy
a peculiarity in the sense that only classical models often have this kind of problems.
Yeah, but third law of thermodynamics does not hold for classical spin systems. As you're pointing out, that it's a law. What it's pointing to is that the real world is quantum mechanical.
So as you're going to T equals 0 at some point,
Consider
you
the
cannot-
Dulong-Petit law. What is Dulong-Petit law? Specifically, it is a constant. Entropy also does not vanish. But that's not true. It's not true because the world is quantum mechanical. As you go to zero temperature, the quantum mechanics shows up, and the density of states. You know the Debye theory, etc. It actually goes to zero. That's another example. In classical systems, you can easily violate the third law, but it's a model system. The third law is about the real world.
good, so we're having some discussion, but discussion is confined to this part of the Okay, so just what I'm going to do is again very simple. Time is running out, so I just want to calculate the energy associated with this. So I'm creating again in the 1D algebraic model, but I did was I created the number, and there was a constant energy associated with that. But then it gets created because there is an entropy factor which is given. But here, it is very easy to show that the energy itself is going to zero. It doesn't cost any energy, so to speak. Okay, this kind of a domain ball, the system size becomes large. So this is what I'm doing. If you, what we were talking about, there was a situation where instead of pi, I call it 2 pi 2 pi. If it goes through the whole thing, then all the averages will be equal to 0. So that factor doesn't matter. So basically, now we have cosine theta I minus theta I plus 1. This is equal to pi by n, or 2 pi over n, or whatever, something that becomes very small when n is large. So, and for each of the terms, you have that cosine. And there are L such terms, L such forms. So that energy will be L times cosine alpha into pi plus 2. This is the energy. Associated with creator J is there. J is square. Now this, of course, when L becomes large, this becomes small. So we can use expansion. So this cosine I'll replace by first term in the expansion. First term is just the ground state energy, J square L times 1. When all of them are the same, we have J square and and then L such bonds, so J squared 1 is the downside energy. And now we have, let's go for Einstein here. Now we have positive energy, which is the excitation. But you see that the excitation energy has 1 over L squared here, there is L here, so there is 1 over L over all the excitation energy. So big system, these excitations don't cost any energy. Whereas for the Ising model, there was always a cost of energy associated with creating a domain ball. Here, this domain ball is basically just as the order, because spins are going from up to down and then going to up again. That order will go away if one create this kind of excitation. And the energy of those kind of excitations will go to 0 in the large L length. So it's even more difficult for this continuum spins to order in one dimension. And in particular, Ising model orders in 2 dimensions. Ising model is a post-Fermat solution which says that there is a critical temperature below which you have 2 long range order. But the XY model, in 2 dimensions, there is no true long range order. You can have order of some kind, etc., which I didn't go into. But the general result is that if you want to create a domain ball, suppose as some limit to that. Here you see that here it's going as 1 over L. When D is equal to 1, then it says that it goes as 1 over L. 2 dimensions, still there is finite energy, it doesn't diverge in 2 dimensions. And same is true for the Heisenberg model. Any continuum spin model will have this property that this kind of domain ball excitations energy will go to 0 as system size goes to 0. And that leads to, in some sense, in a crude way, to this thing that you may have heard about earlier, which is called the Marmin-Wagner theorem. It says that systems with continuous symmetry cannot have 2 long range order in 2 dimensions, 2 order dimensions. Ising model can have long range order because symmetry is not a continuous symmetry. It's just up down, discrete symmetry. Whereas in this case, we are talking about continuum symmetry. And these models cannot order the spatial dimension is 2 or less. So it's important to keep this considerations in mind when you go into the possibility of ordering phase conditions and then stuff like that. So I thought, this is one thing that one can mention in passing, that this kind of consideration, which told us that there is no order in the 1D Ising model, can be extended to other models, and there the ordering becomes even more difficult to have in 1D because of this continuous symmetry. There is also something that is related to what I'm just talking about. It's called, I don't have time to go into, which is called spin waves. We have ordered state, and from the ordered state you look at excitations. Then the excitations look somewhat like this, not quite, because it was looking at already order is there, and then you were looking at small deviations. But these continuous spin systems, these excitations are gapless. In the sense that in Ising model, as I said, go to the first excited state, then there is a gap, 2J. But in continuous case, you can create these spin waves, magnons, whose energy goes to 0 as wave number goes to 0. And this is again, there is something called Goldstone mode and all those things that are related to that. Whenever continuous symmetry is continuously broken, then you have these Laplace excitations. So in the case of ferromagnet and the ferromagnet, this will be spin waves. Okay, so then remaining 10-15 minutes, I will now change the subject. So far we have been talking about ferromagnetism, but in this discrete models. What I mean by discrete is that now the spins are located at lattice sites. These are localized spins at lattice sites. Then you write down Hamiltonian, and then from that you can find out if the spins are going to align or not. There is one more, or not one more, there are many more ways of getting magnetization. but at least something that I thought should be mentioned in this course is that there is something which is called itinerant magnetism. In the sense that here these local moments are sitting at static sites, and then whether they order or not order is a question that we are addressing. But there is something in some systems, you actually have magnetism coming from electrons which are not localized, which are like metallic, which are extended wave functions. So how does one understand that? So again, there is a theory for that, which probably I'll not have time to go into in detail. But I just want to point out some physics related to that. That if you have, let's say, free electron gas, if you have electrons confined in the volume, there is actually a model which is often used in theoretical studies of this, which is called the Jellium model. Jellium model is you have a positive background, and there is a negative electrons are moving in that background, and a positive background is chosen in such a way that the net positive charge and negative charge to cancel each other. Otherwise, you see divergence and things like that. But that positive charge is just towards the background. It is not. It doesn't have any dynamics. Dynamics is just electrons flowing in that background. And then there are some theories of this. But you see, you have done that in some sense. I mean, when you do fixed Fermi gas, for example, then you assume that the energy is just the kinetic energy, and then no interactions, and then fill in single particle energy levels up to the kind of Fermi energy. Here, one goes a little bit beyond that, because electrons, of course, are charged, so there is some Coulomb interaction. That's the sort of generic problem in solid state physics, so to speak. How to deal with a system of electrons which are interactive, how to take into account that which nobody knows how to solve still. But there are various approximations that we will do. So when there are no interactions, then you have the standard picture that you have a spherical Fermi surface. All states inside the Fermi surface are occupied, all states outside are empty. And you can calculate various quantities. And many things actually agree with experiments. So that's one reason why one in some sense does this approximation, because one assumes that in certain circumstances the interaction doesn't matter that much. And there is Fermi liquid theory and all those things are there which justifies that kind of treatment. We'll not go into it.
Yeah, just to go back slightly. So the word itinerant means?
So something that moves around. You know the word itinerary. When you are going from visiting 10 places, then you say that I go there first, go there second. Itinerant means that something which is not localized, which moves around. Question? So I just want to give you some argument which says that if you take into account these interactions, then it's possible to get field magnetism even in this Jellium model. Actually, it doesn't happen. We do a very good calculation, then we find out the Jellium model does not show ferromagnetic terms. But the arguments themselves contain some physics. The same arguments, when you apply them to band electrons, then one does get ferromagnetism. So basically, I'll just tell you a little bit about that argument, and that will be done today. So as I said, we are just looking at that model, free electrons. Good. Actually, I like this one. So if you look at free electrons, then your energy levels are just the kinetic energy, h bar squared k squared over 2m, and then you fill up these levels all the way up to the Fermi energy, then you get to the ground state. When you ignore the electron-electron interaction, free electron basically says that you don't, nothing else is there, no interaction is there. So what do we do? So the calculation that all of you will remember, I'll just write down this calculation. Do you remember this when you do first Fermi statistics? This is what you do. So what I'm doing here is that I'm just integrating over all possible k, going from 0 to kf, three dimensions. So you have 4 pi k squared dk. And this is the factor that is important. What does it come from? The spin degeneracy. Right? So when you assume this calculation is valid, then you assume that n is equal to, of course, n up. And you also assume n up is equal to. Right? And so this factor 2 comes from that. So this is the situation where enough is equal to n down, and then there is no magnetism. It's just total m is equal to 0. If I want to now do a calculation where you have n equal to n, then what will change in this calculation? This factor 2 will go away. Yeah? So the factor 2 to go away, then if you want to get the same number of electrons, of course, then your kf has to go up. Is it clear? The Fermi energy has to increase. We just have only one kind of electrons. What I'm just going to do is to compare the energy of this state with that state and see whether there is any possibility that this may have a lower energy. Yeah? So this simple thing tells you that when I make the system polarized, then this 2 factor is not there. So to get the same n, I have to go to a higher value of kf, and your kinetic energy will go up. So, I mean, just in this case, there is no possibility of magnetization. But one thing that we have neglected here, of course, is the interparticle interaction. Interparticle interaction is the Coulomb interaction. The Coulomb interaction has this form E squared Ri minus Rj. Electronic charge divided by the distance, Coulomb interaction. And this Coulomb interaction, of course, assumes a large value when Ri is equal to Rj. Cannot be Ri, can be diverged, but when they're close to each other, the energy becomes large. So now this considers the spins coming into the picture. If we have both up and down spins, then they can come arbitrarily close to each other. There is no Pauli principle which says that they cannot be at the same side. Right? This again because they are particles. So when you have this situation, there two up electrons cannot come very close to each other, two down electrons cannot come close to each other, but an up and down electron they can come close to each other. So in general, the Coulomb part will give you a higher value when there are both up and down electrons. Yes? So I mean, if you want to reduce the Coulomb part, then it helps to have polarization. In the sense that if, in this case, everything is up, the two electrons can never come close to each other because of Pauli principle. So the electronic part, the interaction part of the energy, that prefers to have polarization. And so I mean, there is competition. That the kinetic energy, so the picture general physics is this, the kinetic energy goes up, but the interaction energy down as you increase the spin polarization. And depending on, one of these things can be calculated very explicitly even for the linear model. There are again various approximations that people want to do. The standard approximation is what is known as the TIFRH approximation that you may have seen in some course in anybody's theory. TIFRH theory says that when the density becomes small, density of electrons becomes small, then actually this state has lower energy than that. So there is a transition from a paramagnetic to a ferromagnetic within TIFRH theory as you go to low density. But TIFRH theory is again an approximation, so one can do better than that. And then in the linear model there is no such transition. But in the electrons in a band, then your density of states etc. will be very different. And so again, there is something called the Stoner theory of ferromagnetism, which says that in some bands, whether the bands such that they are metallic, their electrons are not localized at these points, but they are itinerant. One can have a non-zero polarization, non-zero magnetization in that system. So there is this lattice model that I've been talking about. That's not the whole story. There is also the possibility of having electrons which are spread out over the whole system. They are not localized in individual states. And because of this competition between the magnetic energy and the Coulomb energy prefers them to be all in the same spin state, because then two electrons cannot come to spin state just like all of this. Actually, what happens is that even in the other case, when I'm saying that there is some in up and some in down, then TIFRH theory says that let me not go into that. But up and down electron can come close to each other. Pauli principle doesn't prevent. But the fact that there is a repulsion, that it actually prevents to one up and one down electron also from coming very close to each other. There is energy that is called correlation energy. That is not there in but anyway, so those are technical complications. Physics, you should remember that that's what Musashi also was saying last time, that when you look at exchange interaction, it actually is Coulomb interaction. There is continuity. So even that contributes for itinerant electrons. There is a different kind of magnetism, ferromagnetism that you can have in metallic substances. And that's all I want to say about it, because it's much easier to deal with that.